Okay,
Are you good to go?
I think we're good to go.
Okay. Welcome everyone to the non-ICFP people. Wait, is Ryan going to ICFP?
I'm going a little later.
Okay.
Oh, I thought you were going to be here.
You stayed behind just for this.
Oh, no.
We have a spectacular set of lightning talks. First, we're starting with Aaron, APL styles, anti-patterns, and patterns. Take it away.
Ooh, cool. Nice little timer. Yeah, so this is going to be sort of like a teaser taster for a keynote that I'm giving at Dialogue 17 in about a week or two. And it came about from asking the question of what do expert level APL programmers write? How does it look? What does it look like? And then why do we get this really hard beginner's plateau with people who have programmed before trying to learn APL? So they start to learn APL and bam, they hit this wall, they understand the semantics, they can tell you what the little funny symbols do, and then they can't do anything else. They can't write APL code. And so the question is, why are they doing that, and what's the experience that they're getting different from when experts use APL to really great effect? And so since this is a lightning talk and I was told to give the major takeaway early, here it is. So basically, to cut the whole story short, good APL code exposes the entire picture at a glance in a way that facilitates rapid manipulation, careful analysis, and minimal mental overhead. Now, the important thing here is it's not the big picture, and it's not the abstracted little details. The APL programmer is trying to put the whole stinking picture at a glance in all of its details from top to bottom. And this is where you start to see some differences between the regular style approach and this one. So experienced programmers who are used to working with other languages, but who are novice APL or array programmers in the Iverson style, in order to really make use of the language and figure out how to do the things that you see APLers doing, have to consciously counteract their mainstream programming tendencies to sort of get APL and to actually be able to use it to any meaningful effect. So success, if you want to actually use Iverson-style array programming anywhere, what I found is it's actually more about thinking about what the human experience is, what the programmer experience is, rather than thinking about semantic robustness. And that's probably, since I've been teaching a lot of people who have PL background, this is a really hard hurdle to overcome, and I think it's one of the contributing factors to the sort of beginner's plateau that I see in a lot of people who have prior programming experience with other languages. So a lot of this is derived from work that Iverson did in the 60s, 70s, and 80s about his 5 design principles for language development and notational thinking, things like that. But I've tried to boil it down into something that is a little bit more practical, so going from the higher level design principles down to what I call 8 anti-patterns and patterns. And these are not strictly dichotomies, but they are tensions, sort of like the Agile Manifesto portrays a set of tensions between, say, running code versus documentation and things like this. And my claim is that if you want to do good APL-style programming, if you want to see how to make good APL programs, whether you're using APL or not, you have to actually, in a sense, give up your best practices and replace them with things that appear to be completely anti-patterns to what you're used to doing. And by doing that, you actually get the benefits. If you don't do that, you end up writing Python code in APL, which looks cool, but it really isn't actually gaining you very much. It's almost gaining you nothing except the fun of learning a new language and writing Python in that new language. So we can basically now simmer over these and look at them. On the left side are what, basically I've shown a version of this slide to lots of experienced APL programmers, and they instantly get it. They're like, bingo, exactly, this is what I always do. You show this to other people and they go, huh? So, yeah. But APL programmers find this sort of dichotomy or tension almost intuitive or very second nature to them, the ones who have been doing APL for a long time. So rather than going through anything in particular, we'll just briefly go through them. Brevity versus verbosity, pretty straightforward. Most languages pay lip service to small code, but don't actually do small code, to an APLer's viewpoint. Macro versus micro, a lot of programming languages allow you to have really great control over hiding away the big picture and focusing on the detail that you want at the given time. So like the NanoPaths framework is very good at giving you specific help on ignoring the big traversals that you're doing. Focus just what do we do with this one node when we have this node, right? That kind of thing. APLers, on the other hand, often suppress minor details in favor of seeing the big picture with an explicit understanding of that trade-off. Transparency versus abstraction, this is the one that I love because I like to say in APL, abstraction considered harmful. And it's funny, but it's actually true. As APL is one of the few languages in which I've seen a lot of really good code that's considered good code in the APL community really doesn't have a lot of abstraction. You have the base layer abstraction, and then you have the abstraction at the domain level, where your domain experts are doing their code, and you oftentimes don't have any abstraction in between. And unlike, say, Scheme, the first thing a schemer does is figure out how to not write Scheme and write in their new DSL that they're going to work with. They tend to, if you're really leveraging Scheme, you're building up a set of abstractions to work in the problem domain in the way that you feel is most natural. And then to go on top of that, you have idioms versus libraries. Idioms being these short pieces of code which are simultaneously the full implementation of the code, the name of the code, the symbol of the code, and the thing that you put in the code all at once. And this is sort of like a version of Knuth's re-editable code on steroids. And this is sort of in tension against the tendency to develop libraries, where the main access point is the name, where it's a black box behind it, and so on and so forth. Data over control flow. APL code tends to have relatively sophisticated data representations in terms of multi-dimensional array layouts, things like that, but tends to emphasize extremely simple control flow. Structure tends to be more meaningful in the APL community, whereas names tend to be much more widely used to sort of help you track the flow of code through a regular program. Implicit versus explicit and syntax versus semantics go along with that. Specifically, APLers are perfectly comfortable with type errors. And they're perfectly comfortable with hiding away, edge cases and things that they don't consider matter in favor of prettier code, or code that is more generally usable across the board. So very often you'll write code that, does a lot of things, applies to everyone, but might have little idiosyncrasies here or there, or interesting effects that pop up, or emergent behavior. And the APLer likes that. Whereas most other PL programmers don't like it. They tend to prefer really nice, crisp, clean semantic lines that help you get certain semantic guarantees out of your code. And that's basically it. We've got a few minutes to discuss it, so we'll give this little quote, but we've got a couple of minutes, and I can go into any more detail on any of this if you want, and then afterwards I'm happy to discuss these in more explicit detail, code examples, things like that. But this is Alan Perlis on APL one-liners, and he sort of gets at this idea as well that the what makes APL powerful isn't necessarily anything in the semantic realm or anything in terms of how it behaves, but more the emergent behavior that you see in the human culture that surrounds working with APL, how it changes your mental approach to working with problems. And he calls it sort of lyrical programming, where you're composing things a lot more with the taste and design of sentence composition, rhetoric, that sort of thing, as opposed to building these nice walls and tight structures like you would in other, say, very highly statically typed languages or something like this. So the big lesson is basically, if you want to do well with APL or understand it, you've got to focus on the human experience that you go through rather than just the operational experience that the code is going through. If that makes no sense. I know that is very, very brief, but it is just a taster. They're giving me a whole hour to talk about this dialogue, so I'll be able to explain lots of stuff. But yeah, any questions? Yeah.
I can understand the change of mindset when changing languages. You have to think in that language. Yeah, but you talked about, for instance, abstraction versus transparency.
Yes.
And how we like the abstractions, the other people.
Yes.
And I believe it's not a matter of preference. I believe there's a there is a reason that we like abstraction, and I want to understand whether APL people actually think that it's good not to have abstraction in general.
Yeah, absolutely.
What is the rationale
if you tried to do APL style programming in any other language, you'd be crazy. You'd be bonkers nuts. There's a reason abstraction exists. Abstraction is a good thing, right? However, the reason APLers get away with it is because they're doing something different. And the way the language works and the way they interact with their problems and their code bases is different on a holistic level that changes it and makes transparency tend to sway to the more important side than abstraction. So it's not that the APLer hates abstraction. We do use it. But the way in which it's used is very, very different. And the benefits of being able to see the whole code and expose a lot of details becomes really, really relevant when you're working in that style in a way that I would argue is very difficult to achieve in a traditional programming language, which is why it's not a good thing to expose all that in a language, because what you're working with is very different. Your foundational abstraction is very different. So, yeah. Oh, do we have extra time?
That's your question time.
Oh, cool. I thought we only had 10 minutes for it. All right, cool. So, yes.
I will have a question for everyone, not just you.
Yeah.
But the question I want to invite people to think about is why abstraction, right? So, maybe some of us like abstraction just for abstraction's sake, and they try to say APL.
I like it.
Or when you want abstraction, you don't use APL. But usually, I think for myself, abstraction is not something I like myself. It's something I like that's certain some other goal. For example, the goal of being able to easily change your program when you change your mind.
Right.
That's my usual excuse.
Yes.
Excuse. So, what if that's our excuse, and we all can have different excuses at different times? While maybe there's other ways to achieve that. Maybe APL is, whatever people do by APL programs are another way to achieve the goal of being able, making it easy to change your code when you change your mind.
And in fact, you've hit on the primary difference, right? Abstraction serves a really useful goal in, say, object-oriented programming, which allows you to make changes in one space of the code without affecting other pieces of the code, right? And that's a really valuable thing when you're dealing with an object-oriented programming language and the type of structures that you develop. In APL, like you say, you still want to be able to easily edit the code, but for them, making the code easier to edit means making it more transparent, because making it more transparent often means that they can reduce the edit distance between code site use and definition and the overall size of the code base. And so, for example, by removing a lot of abstraction in my compiler, I can get the compiler down to 2 pages. And when the compiler is 2 pages, I can literally see every use case of any given expression or any given case. And so when I need to change something, I can sort of see the whole picture all at once by leveraging the transparency, and thus it's easy for me to make changes. Whereas I couldn't do that in an object-oriented programming language, which had more verbosity in it. So instead, I would definitely use abstraction there to make sure that I can make changes safely.
But I'm kind of having a hard time buying that argument, because say that you have a large code base and a screen the size of this wall.
Yeah.
Is it easy for you to then?
Well, so in practical code, the baseline at which a static type system seems to become useful in APL is when you hit about 1 million lines of code. So the people who have been able to get benefit out of, say, like a static type system that gives them some level of additional abstractive capability on their code base, they're working at about 1 million lines of APL code. Below that, nobody else has seemed to get a lot of benefit out of it. The cost-benefit analysis doesn't work out really well. And for example, my compiler is taking about the same complexity of what you would get at like a 423 compiler. So it's about between 3 and 5,000 lines of code in like a nanopass style versus 150 in micro. So the difference is the size of code base is really different. So yes, it does become matter when your code base gets large enough, but the types of problems you're dealing with when your code base gets that large, you're working at a very different scale. So when I'm looking at a page of APL code, I could be looking at a system that's 1,000 or 2,000 lines, 5,000 lines long in another piece of code. And so the difference is partly in that shape, the way you look at it.
All right, thanks, Aaron.
That might work?
Yeah. All right, good. All right, next up is Ryan Scott. Type Theorists Hate Him. learn this one weird trick to fake dependent types in a language that doesn't
I hope
support
that
them.
works.
Learn the truth now. Ryan.
Thank you, Ambrose. So I picked this title because, you know, in the spirit of annoying advertisements you see on Facebook, I'm going to be the annoying guy that advertises Haskell today. So yeah, we're talking about languages that do and do not support dependent types. So let's pick an example of a language that does support them, like Idris. So this is like the simplest example of a program I could think of that leverages dependent types somehow. So we have this function make single, and it takes a bool as an argument, call it x, and depending on whether x is true or false, it's either going to return a nat or elicit nat. So that's cool, right? We can have our return type depend on the value of an argument. That's pretty sweet. So the question is, can we take this example and convert it to Haskell? Well, I mean, syntactically, there's not a lot of changes we have to make. I mean, we have to like take that single colon and turn it into a double colon, and then turn the word list into square brackets. But otherwise, it seems like it should be straightforward. But unfortunately, it's not actually straightforward. I mean, one problem is that it just doesn't parse, which is kind of annoying. But I mean, the bigger issue is the fact that we're trying to lift this if expression to type level, and that's not something that Haskell has built-in support for at the moment. So if we want to emulate a programming practice like this, we have to get a bit more creative. So our solution to this problem is going to be through the use of singleton types. And in order to use singleton types, we need to enable, you know, a couple of GAC extensions.
When are we getting language symbols?
When someone gets annoyed enough to implement them. You know what all these do. Basically, we're not using vanilla Haskell here. We're going into deep Vanguard GAC territory, so it's going to get weird. So I mentioned we're using singleton types, and what that actually means in terms of code is this thing. So if you're not familiar with data families, don't worry. Essentially, this is a family of types that's indexed by a kind variable k. So to give you a concrete example of what that looks like, here is the singleton type for pools. So here we're instantiating the kind k with the bool kind. And it has two constructors, s false and s true. So it looks pretty similar to a regular Boolean. The only difference here is that we're instantiating, oops, sorry, I went ahead too far. The only difference here is that, like, in a normal constructor, you would return something like sing a. But here we're using a generalized abstract data type, or a JDT. So we're taking the return type and we're producing local evidence that the return type is equal to something. So in the s-false constructor, we have evidence that the return type, which we call a or something, we have evidence that a is equal to false. And in the s-true case, we have evidence that a is equal to true. And this will become important later. An alternative way you can define this, if you don't want to use JDT syntax, is to use a more conventional syntax for Haskell constructors. I say conventional because, I mean, we require a bunch of extensions, but what else is new? But here it makes it explicit that we have evidence that the return type is equal to false or true, which evidence is denoted by that tilde symbol. So that's how you define the singleton type for pool. By the way, singleton, that term comes from the fact that if you have a monomorphic singleton type, then there should be exactly one inhabitant of it. So for example, sing false, the only inhabitant is s false, and for sing true, the only inhabitant is s true. Here's one more example to give you a flavor of the kind of appearance that singleton types take on. So here we have a simple definition of piano natural numbers. You either have 0, z, or a successor of some nat. The singleton for nat is going to be either sz, which has evidence that it's equal to z, or it's going to be ss, where it takes some singleton natural number n, and then produces a singleton that's 1 greater than it. And if you want to see that with the other style of syntax, then here it is. Here it makes it obvious that we're quantifying over another variable in this constructor. But otherwise, it's pretty similar to the previous example we saw. Okay, so we're going back to our earlier example. We need some extra secret sauce in Haskell in order to write something like this. So using singleton types, we get part of the way there, but we're missing one more piece, which is the ability to take an if expression and lift it to type level. So being creative, clever programmers, we will solve this problem by using type families. Yeah, that definition looks kind of weird. I mean, it's Haskell. It's the best we can do. But if you stare at this, it looks pretty similar to how you might intuitively think of an if expression reducing. Don't worry about weird details like order evaluation. It's not important here. What we have, it is important, is that if it's true, then we get the true case, and if it's false, we get the false case. And that's fantastic. So equipped with singleton types and our if type family, we can actually write make single in Haskell, which is really nice. So all we need is a sing over a bool argument and the if type family. So you might be asking, well, how is this possibly type check? The trick is the fact that we're pattern matching on S true and S false in its definition. If you pattern match on S true, remember that you get local evidence that X is equal to true, and because X is equal to true, this allows this type to reduce to nat. So if you put a nat here, it'll type check. Sweet. And in the other case, if you pattern match on S false, you get evidence that X is equal to false, so that allows it to reduce to a list of nats. So in either case, it type checks and everything's all groovy. So if the name sing weirds you out, here's another way to think of it. A sing is basically a pi type. And in fact, you can literally define pi to be sing in Haskell, and it all works out. So if it makes you sleep better at night, just think of sing as a dependent quantifier, and don't think about it too hard. So unfortunately, I only had 10 minutes, so I don't have time to go over all the examples of crazy things that you can emulate in so-called dependent Haskell. So I'll go over one more example. So in dependently typed languages, you can do this nifty thing with dependent pattern matching. So I had to include length index vectors somewhere in this talk, so here it is. You either have nil, which has length 0 or z, or cons, which takes some vector and adds s to the length. So that's pretty straightforward to find. And here's an example of a length function on vectors, but this doesn't actually show off dependent pattern matching so much. If we want to do that, we can use this alternative definition instead. So here, we explicitly name the n variable, and we're using curly braces here because it's not an explicit argument to the function. However, despite that, you can actually pattern match on it here. And I'm using dependent pattern matching because you'll notice that there's actually like 4 different combinations of this n value and the vec value you could possibly think of, right? It's 3 times 2 equals 4. We don't actually have to list all of them because the type checker is smart to figure out that the other 2 cases wouldn't type check anyway. Like if you tried to combine length z with cons, that wouldn't type check because the length has to be at least 1. And similarly with length being s and the vector being y. So that's cool. So can we fake this in Haskell? Actually, it turns out we can. So turning the vector type into Haskell is not much work at all. Again, we just have to turn some single colons into double colons. And then to actually write len, instead of pattern matching on n, you just have to pattern match on a singleton type. So that's possible, and that's cool. And the GEDT type checker is smart to deduce that you don't need to write all 4 cases. So this will compile without lens. But you'll probably notice I'm cheating a bit here because n is no longer an implicit argument. It's an explicit argument. So in true Haskell tradition, we will solve this problem with a buttload of type classes. So we're going to introduce a sing I class where the I stands for implicit. So given some type A of kind k, we will give you the unique singleton inhabitant of it, which we call sing. So if we're in the context of nats, there's only 2 sing I instances we can possibly make. One is where the type is z. In that case, we return at z. And the other instance is where the type is s of n for some sing I instance n. And there you return ss on top of sing. So with sing I in hand, we can write a variation of this function that doesn't pass n as an explicit argument. And here it is. All you have to do is just call ling on the sing that you get. So we accomplish it. Now, we lost the fact that we're explicitly pattern matching on it, but I mean, it's a hack, right? Bear with me. So unfortunately, I'm out of time. There are a lot more crazy things you could do with singletons and the like in Haskell, but if you want to get some more info about this, I encourage you to come to my Type Theory reading group talk 2 weeks from now, because I'll be talking about going the other direction, where instead of using singletons, you can come up with a design that will obviate the need for singletons entirely. And if you want to learn more, there's also a package on a package that has a lot more crazy tricks, like they've taken a good chunk of the base library and lifted the type level using singletons. It's pretty crazy. I encourage you to take a look if you're feeling really masochistic. So that's all the time I got, so I'll turn the floor over to questions. Yeah.
So in that last example, did we even need the instance for sing I?
I think you don't technically need it, but I mean, if you didn't have those instances, you called the call length prime, then you would probably get an instance resolution error, so it wouldn't actually be useful in practice. So I show the instances there just for completeness sake.
So from the comps, we determine we can also refine the index unique, right? From middle, we can possibly.
Right, yeah, you'll know what the length turns out to be when you pattern match on a nil or cons, but the thing you need the sing I instances for is figuring out what sing values to produce out of nowhere. That's where the implicit magic comes in.
So because we're taking, so we don't always.
Or maybe what you're asking is like, in this.
What I'm claiming is that we didn't need the sing I at all. We could just pattern match on the back and get our answer.
Oh, I see. So if we were in a properly dependent type language, then we wouldn't need to, correct? However, keep in mind, this is not a definition, or maybe I don't understand your question properly. I think maybe we should take this question offline, because I think there's some subtlety here that I won't grasp in the 2 minutes I have. Yeah.
What's the line count of the singletons library versus the line count of the Idris library?
Surprisingly, I'm willing to bet that Idris is larger, but I think that's because it uses Pascal. So take that.
So it's all Haskell.
Like 60%, but I mean that 60% is like 80% if you really look at it. Yeah.
And is this like a mountain, like we do it because it's there and we can?
Well, if you say we, I think the more accurate noun to use there is Richard Eisenberg, who saw the mountain of writing dependent types in Haskell and came up with singletons as like an easier way to trek across the hills that he came across. But
He was coming across
I think his ultimate goal is to get rid of singleton types in the end. But that's at the moment we don't have the technology we need to cross some of the the spikier hills along the way. So this is the makeshift solution we have for the time being. Yes. But I mean, it's also cool and so right as a way to just very crudely retrofit dependent types onto something that has a bazillion extensions that get you 60% of the way there, but not quite there.
Right.
So it's an exercise in that sort of. Any other questions?
All right, let's thank the speaker.
Thank you.
Aaron. Okay, so next up we have Vikraman, and he's talking about homotopy theoretic aspects of reversible computing. Here's your time.
And then is that I or I?
Yeah, it's not right.
Okay.
Let's see. All right, so the first slide is actually a pun on an old paper from 2008 by Michael Warren, which was the first paper that connected type theory with homotopy theory. And this is the first work that connects reversible computing with homotopy theory, hence the name. Okay. So there are many people who have worked on this with us, and I think some of them are also in the audience. So when I'm saying reversible programming, I'm specifically talking about a particular family of languages which was invented by Amr and his students in 2012, 13, 14. It's called Pi, which is a confusing name, but okay. So the question is what? So just like simply typed lambda calculus has models in Cartesian closed categories, what are sound and complete models for this language Pi? And of course, in 2012, 13, 14, in parallel, there's also the univariate foundations and homotopy type theory. So the other question is, what does completeness for Pi have to do with univariate univalence axioms or homotopy type theory. So this is a possible solution. Okay, so on the left we have pi and various fragments of pi. So the first one, pi2, is a fragment of pi which has reversible programs on 1 bit. Pi n is reversible program on finite bits. Pi half is something called a fractional type, which is half a bit, but I won't go into that. But okay, so the talk today is about the first part, which is so it's a model for pi2 in homotopy type theory, which corresponds to an infinity group-wide or a topological space up to homotopy. So the reason I'm showing this is not to confuse you, but to show that type theory can make our lives easier. So I don't need to worry about infinity group-wides or higher dimensional spaces, but instead just work internally in model. So okay, this brings me to my first slogan. So in the immortal tradition of Lauvier and Lambeck and Scott, category theorists like slogans, and I like slogans. So my first slogan to everyone is that internal logic is better than external logic, which is what programming languages is all about. So when we write programming languages, we work in the internal logic of some category, where things are correct by construction. So yeah, okay, that's my slogan.
I'm trying to make sure I understand. So this is basically saying everything should be first class. Is that how programming language people talk?
Yeah, kind of. Yeah.
Don't just have functions. Have functions as values.
Yeah, sure. Okay. Like I don't want to look at functions externally. Instead, I build up functions in my theory. Okay. Let me fix some notation. It might be confusing, but so if if T is a pointed type, suppose star is a point in T, and I define the loop space of T to be the space of paths on star. Okay. Automorphisms on T are the equivalences bit on T. Okay. I call this type B odd because there is some connotation to what it means actually. So it is the type of types which are weakly equivalent to T. Okay, and then there is a type called the singleton subuniverse of T, which is the type of types which are equal to T. Okay. So if you have not seen propositional truncation before, it's something in homotopy type theory. So it means that it's a sigma type, but you only get access to the first constructor, and the second constructor is truncated, which means you cannot look into what's inside or use it to do more computation. So for example, what's a term in the singleton subuniverse T? So you can just choose T, and reflexivity gives you a path to compute. Okay, so we all know the univalence axiom, but I'm going to talk to you.
Sure.
Oh, okay. I mean,
This we is referring to the tricycle.
I mean, univalence axiom is pretty popular. Right? Okay, but I'm going to talk about a generalization of the univalence axiom, which is about fibrations. So Rand showed us some dependent functions, but type theorists call them fibrations, or homotopy type theorists at least call them fibrations. So any type which is varying over A and picks out some types in the universe, it's a type family or a fibration. So if you know substitution in Idris Agda, so in homotopy type theory it's called transport. So you can transport paths in the base space A to paths in the fiber. So if you have the path x equal to y in A, substitute x for y, and px goes to py. Also, x equal to y implies y equals x, so you can go from py to px. So using those two functions, you can show that px is equivalent to py, which is what this map omega is. So I'll say that p is, so this type family P is a fibration, and I'll say that P is a univalent fibration if omega is an equivalence. So omega goes in one direction, but if it also goes in the other direction, and they are inverse, then it's a univalent fibration. And this is something from a very complicated paper which was published in 2015, but just a small instance of it. Okay. And this brings us to what the univalence axiom means. So in the previous slide, if you chose Px equal to x and Py equal to y, that's identity fibration, you would get that x equal to y is equivalent to x equivalent to y. So the identity fibration is univalent, which is Wonks univalence axiom. Okay. All right. So I'm going to if your type theory has univalence, then you say that you have a univalent subuniverse. You have a univalent universe. So what does it? So in type theory, you can define Tarski universes, where you have a code for the universe and a decoding function which takes you back to the universe. So EL is a fibration, right? And we'll say that this Tarski universe is univalent if EL is a univalent fibration. Okay. Now, here's a theorem that we prove. So pick any type T and take that type which I defined earlier. That picks out a subuniverse, and that subuniverse is univalent. Okay. And this has an important corollary, which is important for us, which is the loop space of this singleton subuniverse is equivalent to the loop space of V out of T, which is equivalent to automorphisms in T. And I'm going to use this now. So,
What is a loop space?
Okay. Loop space is you pick some point in your type. It has to be a pointed type. They take the identity type from that point.
Right.
So all loops on the Okay. So
I actually think so. I'm surprised.
okay, so take T to be bool, and you get this. So now the problem of characterizing the loop space of the singleton subuniverse is the same as characterizing the automorphisms of it. So 2 is Booleans. How many automorphisms does Boolean have? You have the identity function and not, right? So this is a theorem which informally seems true, but it's difficult to prove in type theory. So how does one prove this? Well, here's an important thing which I think is very important. Right? So everyone in set theory class, everyone studies the Cantor-Bernstein-Schroeder theorem, which says that if you have an injection and an injection, it's a bijection. But this is not true in orthoopposites. So the CBD theorem does not. So it's just an instance of how category theory can open up your mind, right? So the Cantor-Bernstein-Schroeder theorem is not true in all categories, but the converse of it is true in all categories. So if you have an isomorphism, you can build up an injection. Okay. So suppose F is an equivalence. Do we want to show that F is either ID or not? So first prove the general lemma that if F is an equivalence and F is an injection. So F true equal F false implies true equal false. And true equals false can be shown to be inconsistent inside marginal type theory. So, and then use function extensionality to show that F is either ID or not. Okay. So that means there are only 2 automorphisms on 2. And we know that 2 is a set. So automorphisms on 2 is a set, which means there are no 2 loops. Okay. And so using this model, I'm going to claim that the singleton subuniverse is a model for pi. So how do you prove soundness on completeness for a complicated language like this? So in set theory or in like first order logic, it's just terms which you interpret and show that you can go back. But these things have higher order structure, right? So so in programming languages we talk about denotational semantics, but in fact denotational semantics was invented by the logicians in 1960s. So Lovier has something called functorial semantics, and this is a diagram which shows the functorial semantics. So you have your category of syntax, category of models. You build a functor from the syntactic category to the model category, and you can build a functor from the model category to your syntactic category, which is the language functor, and this is the context functor. And they can be shown to be equivalences or adjoints. Okay? So in homotopy type theory, functions are functors. So you just write a function, it's a functor. Okay? This means for pi, we can build up infinity functors between a groupoid and this model. So we did that, and this is all formalized in Agda. So for level 0, level 1, level 2, and after level 3 it gets truncated. And you can check out our paper on the archive or follow our formalization on GitHub.
All right, 4 minutes and 15 seconds of questions.
Go back to the slide where you had the functors between syntax and models. Before that, actually, just it had diagram arrows. Did the names con and lan mean something particular here?
Lan means the language functor, and con means the context.
Ah, okay. I thought lan was like left con extension or something. I was curious. Okay, thank you.
Yes, I mean, depending on how you choose your code. So like, so task universes are weak. So they don't preserve binary types. But if it's relevant, so you can say that any identity class will be the same as the one. There's a page about weak task universes on the internet.
Any takers? Yeah.
What does the upside down pie mean in slide 2 or 3?
Is that the U?
Maybe it was a U. That one, right in the infinity gridwood. That's co-product. Yeah, co-product. Gotcha. Wait. So, infinity gridwood 2.
Okay.
I see it.
Yeah. Wow.
Valid APL.
So, I love research like this because then I can point to this and say, APL isn't so crazy.
No one? All right. Thanks, Vikraman. If any of these talks have interested you, please catch up with the speakers. Otherwise, eat the food. Thank you.
Both.